today we're going to be covering Boolean algebra. I'm sure my colleague covered truth tables with you guys. So, quick little fact: this is the person right here, the person that created Boolean algebra, George Boole. So, he was the one that founded Boolean algebra. He was a mathematician, a philosopher, and he's also the first professor for mathematics at Queen's College, so all the way in Ireland. So why do we use Boolean algebra? We use it to simplify our complex expressions into simpler form. Why is this important? So when we're making our physical components for our chips, fewer logic gates means reducing the size of our devices. We can also make it more power efficient, and fewer gates also means faster speed as well. So making the computer faster and reducing the time it takes for a signal to travel. So before we get into that, I'm sure you guys covered, this is the end of chapter 1. So first I'm going to go over how to draw a few of the logic gates we have. So first we have an AND gate. So an AND gate, how do we draw an AND gate, right? So this is a 2-input AND gate. Basically one input here, another input here. Basically we just have to draw this type of shape. So this is an AND gate. And then if we were to draw a NOT gate, or also known as an inverter, this would be a 2-input NOT gate. It would be like this, and then a triangle with the dot. All right, so that's a NOT gate. And then for an OR gate, we got this, so 2-input OR gate, and then we gotta curve it over here at the ends. There we go. So that's our OR gate. So these are the three base logic gates that we're going to use. Sooner or later, we're going to be learning NAND gates, NOR gates, XOR gates, and a couple more logic design and ICs. So these are just the three simple ones I wanted to discuss. So back to Boolean algebra, right? So this is the first thing. This is the NOT operator. So like I showed you over here for the gate right here. So this is a NOT gate, right? So the NOT operator is basically, we can identify it using an apostrophe or this par kind of symbol on top of the X. So the same thing applies for Y as well. So Y apostrophe or Y bar. This is how we identify or write down a NOT operator. So if you want to invert something, this is how we would do it. Second, we have an AND operator. So an AND operator can be written as XY or X dot Y. Same thing is like how we would normally write it when we're multiplying two numbers. And in this case, for an AND operator, I'm sure you discussed in the previous video, but the only way the outcome can be 1 is when both X and Y are 1, right? So the only case where the outcome is 1 is when X or Y are both 1. Next, we have an OR operator. So this is how we normally do addition, right? We use a plus symbol right here. X plus Y, pretty straightforward. Same thing goes for Y plus X. Okay. So say this is X is equal to 1 and Y is equal to 0. The outcome would be 1 in this case, right? All right, now we're going to postulates, right? So the first postulate is X plus 0 equals X. So I'm just going to be going over the most important postulates that we're going to be covering in logic design. So the first thing is X plus 0 is equal to X. So what does this mean? If you were to add 0 to anything, it wouldn't change the value. I mean, this is pretty straightforward. This is self-explanatory, but I have an example right here. So F is equal to A plus B times 0 plus C times 1, right? So this would just be A plus B times 0 is 0 plus C times 1 is C. So it will just equal A plus C. So it's pretty straightforward. This is just normal addition rules. If you were to add 0 to any number, it would the previous number would be the same. The second postulate, part B of postulate 2, is x times 1 is equal to x. So this is also a common rule, a common multiplication rule. So if you were to multiply a number by 1, it would still remain the same, right? So x times 1 is equal to x. 4 times 1 is equal to 4. Pretty straightforward. Postulate 5, right? So this is where things get a little complicated. We use our not inversion, right? So x plus x prime or x naught is equal to 1. So what does this mean? If you were to have a number and its inversion and you were to add it together, it would equal to 1. So here I have an example, right? So a plus b plus a plus b prime. So this is the normal number or expression, and then here I invert the entire expression. So this is also equivalent to writing a plus b with the whole bar over its top, right? So what is this equal to? So it equal to 1. So this rule is pretty important, especially for simplifying, because once you get a lot of ones, it helps reduce your expression and makes it easier for you to design your whole logic diagram. The next one is postulate 5, part B. So x, when you multiply a variable by its inversion, it's equal to 0, right? So if you were to do, say, x is equal to 1 in a case, right? So x is equal to 1 and 1's inversion is 0. So 1 times 0 is 0. And then say x is equal to 0. This would be 0 times x inverse. So invert the 0 would equal to 1 and then 0 again. So this is pretty straightforward. Now we're going to do the theories. So first we got x plus x equals x. It's pretty weird, right? So x plus x equals x. So how come x plus x is not equal to 2x, right? But for simple logic design, we do x plus x is equal to x. So in this case, we have a f equals a plus b. So what does this mean? We know that a plus a is equal to a because of this theory. So this would just be equal to f equals a plus b. So this is that simplified. The next part is part B of theorem 1. So when you multiply x with x or any variable by itself, it would equal to x, right? So we had this example right here. F is equal to c times c again. So we know over here that c times c would equal to c, right? So then we input this back over here, c, and then bring this down times c. And then again, we go back here, c times c is equal to c. So at the end, f is just equal to c. Now for theorem 2, we go into x plus 1. So adding 1 to a variable, right? So we just need to understand that Boolean logic is completely different to normal math, the one we learned in middle school. So we just need to understand that it's not the same, because if you were to add, say x is equal to 4 plus 1, it is not equal to 1, right? That's wrong. But this is just zeros and ones, so computer logic. So x plus 1 is equal to 1. So let's solve this example right here. F is equal to a times b times c plus 1, right? So this entirely, if we were to simplify, we would put a times b times c plus 1 into brackets. This would just equal 1. Pretty straightforward. So if you add any expression, have any expression and add it to 1, it will just equal 1. This is pretty straightforward. Theorem 2. So when you multiply x times 0, it would be 0. This is normal multiplication rules. If you were to multiply a number by 0, it would just be 0, right? So we have an example right here. A plus b plus c times 0. So if you multiply this entire expression by 0, you would get 0. So De Morgan's theorem, right? So this is a pretty important part of logic design, and you're going to be using it quite often to reduce the amount of wires you have, and when you're especially working with NAND gates, right? So x plus y bar is equal to x bar y bar. So the way I taught you, you can also write it as x plus y, put a huge bar right here on top, equals x bar y bar. And then the second theorem, so we got part A, B. So you can memorize these. These are pretty easy to remember unless they're given to you by your instructor. So the second one is xy bar is equal to x bar plus y bar. So this is also, it can be written as xy bar equals x bar plus y bar. Pretty straightforward, right? Let's convert this into the bar. Right? Okay. So which one will we use? So we know De Morgan's, the first part is kind of shaped like this, right? So we're going to use that one. So what is that theorem? X plus y bar equals x bar y bar. Right? So this would be like the x, and this expression right here would be the y. Right? So A is already barred, so A bar bar times y, and y is b times c bar. So it would be bar. So what happens? This gets canceled out. This gets canceled out. So the final expression is literally just A times B times C. So that's pretty much it for Boolean algebra. I'm going to try to cover all the simple questions. If you guys have any questions, let us know, and we will be more than open to solve it for you. So thank you for watching this video.